Last episode we put together this very basic second order filter. And even though it's really just made of 4 components, the results were actually quite decent. But since the goal here is to build a fully featured VCF with resonance, we'll have to make a whole load of additions and alterations to this design. To start off, let's turn this from a passive into an active filter. Why is that necessary? Well, first of all, I wasn't being completely honest about the performance of this design. While it's tempting to think that simply chaining 2 passive filters gives you a true 2-pole response, this is sadly not the case. To understand why, we'll have to go back and re-examine how those individual stages work. As we discovered last time, the filtering process is basically just an interplay between a resistor and a capacitor. Whenever the voltage on this side quickly rises, a current will be pushed through the resistor and into the capacitor. As the capacitor fills up, the voltage on this side slowly rises as well. Now, as long as that interaction is undisturbed, everything goes according to plan. And I haven't made this clear last episode, but by listening in through an amplifier, we were able to ensure that. This is because amplifiers use voltage sensors to pick up signals. In our water analogy, this means that if we connect this point to our amp, no water actually leaves the pipe system, because the amp's sensor can read pressure levels without interfering with them. Now, if we chain 2 of these filter stages, the story changes quite a bit, because where before this filter's output was completely sealed shut, now there's an opening there, meaning that current can leave through here while the capacitor is filling up. This, of course, is messing with the way this first filter stage operates. But it also affects the second stage, because that second stage only gets the scraps of the first, the current that spills over. Because of this interdependence, the whole filter's performance suffers as a result. Instead of a real 2-pole response, we get something much less cleanly defined. How do we fix this? You guessed it. By adding amplification to both stages and turning this into an active filter. To do that, we have a variety of options, but for simplicity's sake, we'll go for the classic solution, using operational amplifiers, or op-amps for short. These might seem intimidating at first, but they're actually quite easy to understand and use. The basic concept is this. Every op-amp has 2 inputs and 1 output. Think of those inputs like the pressure sensors I talked about earlier. You can attach them to any point in your circuit and they will detect the voltage there without interfering. No current flows into the op-amp's inputs. That's why we say their impedance is very high. Near infinite, actually. Okay, but why are there 2 of them? The key here is that op-amps are essentially differential amplifiers. This means that they only amplify the difference between their 2 inputs, not each of them individually. If that sounds confusing, let's check out a quick example. So we'll imagine that this sensor, called the non-inverting input, is reading 8 volts from somewhere. The other sensor, called the inverting input, reads 5 volts. Then, as a first step, the op-amp will subtract the inverting input's value from the non-inverting input's value, leaving us with a result of 3, because 8 minus 5 is 3. This result then gets multiplied by a very large number, called the op-amp's gain. Finally, the op-amp will try to push out a voltage that corresponds to that multiplication's result. But of course, the op-amp is limited here by the voltages that we supply it with. If we give it minus 12 volts as a minimum and plus 12 volts as a maximum, the highest it can go will be plus 12 volts. So in our example, even though the result of that multiplication would be huge, the op-amp will simply push out 12 volts here and call it a day. The handy thing about op-amp outputs is that they draw their power directly from the power source. This means that they can supply a lot of current while keeping the voltage stable. That's why we say an op-amp has a very low output impedance. Why is that helpful? Well, if we set up an op-amp like this, we can use it to buffer the voltage at our first filter stage's output. Buffering in this context means that we provide a perfect copy of a voltage level without interfering with that voltage level in the process. That copy can then be fed into the second filter stage. This way, both stages are allowed to work in complete isolation without any interdependence, improving our filter's performance along the way. The buffering process itself works like this. We use the non-inverting input to probe a voltage, while the inverting input connects straight to the op-amp's output. This creates what we call a negative feedback loop. Think of it this way. We apply a specific voltage level to the non-inverting input, let's say 5 volts. Before the op-amp starts processing the voltages at its inputs, the output will be switched off. This means that output and inverting input sit at 0 volts at first. So then, the op-amp will subtract 0 from 5 and multiply the result by its gain. Finally, it will try and increase the output voltage to match the calculation's outcome. But as it's pushing up that output voltage, the voltage at the inverting input will be raised simultaneously. So the difference between the two inputs is shrinking down. Initially, this doesn't matter much because the gain is so large. As the voltage at the inverting input gets closer to 5 volts though, the difference will shrink so much that in relation, the gain suddenly isn't so large anymore. Then the output will stabilize at a voltage level that is a tiny bit below 5 volts, so that the difference between the two inputs multiplied by the huge gain gives us exactly that voltage slightly below 5 volts. And this process simply loops forever, keeping everything stable through negative feedback. Now, if the voltage at the non-inverting input changes, that feedback loop would ensure that the output voltage is always following. So that's why this configuration works as a buffer. The output is simply following the input. All it takes then to convert our passive filter design into an active one is adding a buffer after every stage. It's a small change, but quite effective in improving performance. To try this out, I'll be using this chip called the TL074. It contains 4 discrete op-amps, and although this might seem like overkill for now, we'll be needing all of them later on. Setting the chip up is really straightforward. This pin connects to the positive supply rail, while this one gets the negative rail. Providing those rails, in my case, is a self-built dual power supply which puts out plus and minus 12 volts. Then we can use any of the 4 op-amps as we like. By the way, if the whole thing with negative voltages is new to you and/or you don't have a power supply to follow along, check out my video on how to build your own. So I'll simply add the chip to the breadboard, patching in the buffers after each filter stage's output. And that's it, we have an active filter. Let's send in a square wave and see how it performs. Looks a lot like before, though I think the filtering sounds a little cleaner. So far, so good, but a filter is not quite complete without resonance. It's what gives it that typical futuristic sound after all. Let's check out a quick example. Here's a lightly filtered square wave without any resonance. And here's what happens if I turn the resonance way up. The filter seems to be adding something to the sound. And here's how that's normally visualized. As long as the resonance is completely turned down, the filter will simply remove the frequencies above the cutoff point without doing anything else. But as we turn the resonance up, the filter will also start to amplify the frequencies around that cutoff point. So instead of just removing frequencies, the filter starts to also emphasize some. Unfortunately, this type of visualization doesn't really help us figure out how to make our filter resonant. Yes, we know that we have to amplify these frequencies around the cutoff point, but how do you do that? To get a better idea of what resonance added to a waveform actually looks like, let's check it out on the oscilloscope. So here's the same lightly filtered square from before. And here's what happens as I turn up the resonance. Something weird's going on with the rising and falling edges of the waveform. Let's zoom in to get a better idea. It looks like as if the wave has trouble stabilizing at the peak voltage level. Where normally we have a nice and smoothly rounded edge, now we get this over and undershooting behavior that only settles down over time. And as I turn up the resonance further, this behavior only gets more intense. Also, if I lower the cutoff point, the wave stays in the individual over and undershooting phases for longer and longer. So this gives us a rough idea about what separates a non-resonant from a resonant filter. While the former does its job, namely filtering, in a precise and controlled manner, the latter really struggles with that task. It seems like as if the resonant filter overreacts to any sudden change in voltage at its input, leading to this sloppy, bouncy behavior. But that bouncy behavior is not random. The time spent in the over and undershooting phases is constant as long as the cutoff point stays in place. So it's safe to assume that the frequency of this added oscillation is directly tied to the cutoff point's frequency. If that's the case, the notion of the raised cutoff point starts to make sense. Resonance then is basically just the filter itself swinging at its set cutoff frequency in addition and reaction to the oscillation it's supposed to be filtering. As our oscillator swings, the filter swings along at its own pace. And while this might seem very tricky to implement, in its most basic form it's actually really simple. All we have to do is route the filter's output to this normally ground-connected leg of the first filtering stage's capacitor. In case you're confused about what this does, let's analyze this entire circuit step by step. We'll once again keep track of the in and output voltage levels down here. As always, we're assuming the input signal to be a square wave. Then we can expect the voltage here to rise to 5 volts very abruptly, causing a current to flow through this resistor and into the first capacitor. This is possible because the filter's output rests at 0 volts in the very beginning. The thing about op-amps is that they are not only able to push out current, they can sink current as well. So 0 volts at this point is virtually the same as a straight connection to ground. The capacitor can basically expand into the op-amp's output, allowing it to be filled up the same way as before. But as the capacitor fills up, the adjacent op-amp will start raising the voltage at its output, forcing a current through this second resistor and into the second capacitor. This in turn will cause the next op-amp to slowly raise the voltage at its output. And since that output is connected to that first capacitor, something odd happens. A voltage starts pushing up from below. Now, as long as that voltage is still relatively low, current will keep flowing through the resistor here and into the capacitor, though at a slower and slower rate because of the pushback. As that pushback increases, the voltage here will be raised to 5 volts. Under normal circumstances, this would be the peak voltage level. But since it takes some time till the filter's output has reacted to whatever happens here, it will keep raising the voltage. And as that voltage pushes harder and harder up against the capacitor, the voltage at this point will be raised beyond 5 volts. We are effectively creating an overpressure here, which in turn will see an additional delayed rise in voltage at the filter's output, pushing the voltage here even higher. This cascading effect will drive the output way beyond 5 volts. And it would keep doing that indefinitely were it not for the resistor here. Because since the voltage here is now lower than the voltage here, current will start flowing out of the capacitor and through the resistor in this direction. And as the capacitor now fills up from below, the pressure here will slowly begin to fall due to the resistor acting like an equalizing valve. This kicks off a cascading effect in the opposite direction from before, because a drop in voltage here will cause a delayed drop in voltage at the filter's output, which in turn takes some pressure off of the capacitor, lowering the voltage here even further. Eventually, we'll even drop a fair bit below 5 volts, which means that the current here reverses its direction and the whole process repeats. But since this time we're not starting with a completely empty capacitor, the cascading effect has decidedly less time to ramp up, and as a result, won't push the voltage as high as before. Over time, the over and undershooting will slowly fizzle out as the voltage stabilizes at 5 volts. And that's it, we've made our filter resonant. By now, it should have also become clear why that resonance causes the filter to swing at its set cutoff point. The time spent in the over and undershooting phases is directly determined by the capacitor sizes and resistance values, which in turn also determine the cutoff point. But enough theory, let's see if this actually works. So I'll simply route the filter's output to this leg of the first filtering stage's capacitor. And yeah, that works as expected. You can clearly see the over and undershooting behavior if I zoom in a bit. So far, so good. But with this implementation, we have no way of adjusting the amount of resonance. So let's figure out how we can change that. Earlier on the oscilloscope, we saw that an increase in resonance equates to a more intense over and undershooting behavior. So it's safe to assume that adjusting the amount of resonance can be done by in or decreasing the amount of feedback we apply to the capacitor. Because the more intensely the voltage at this point changes in response to a change in voltage here, the stronger the cascading effect will be. But before we go about increasing the amount of feedback, let's first try decreasing it, since that is a bit simpler to pull off. All we really need to do is scale the filter's output down before sending it to the capacitor. How do we do that? Easy. We use something called a voltage divider. Now, I won't go into complete detail on how those work, because I've already done that in my DIY VCO series. But here's a quick rundown. If you set up 2 resistors like this, with this end connected to a voltage and this end connected straight to ground, you can pick up a new divided down voltage from this point. The relation between the 2 resistors will determine the fraction you'll get. If both are of the same value, the output voltage will be exactly half of the input voltage. Since we'd like to change the voltage on the fly, using 2 fixed value resistors is not really an option. But thankfully, we already know the ideal solution for this problem. Remember how last episode we said we'd ignore our potentiometer's third connector? Well, now it's time to look into it. At its core, a potentiometer is constructed like this. There's a round track of resistive material that connects the first and third connector. The resistance value of that entire track is what's used to classify a potentiometer as a 10K, 20K, 100K. Now, the trick is that the second connector is hooked up to something called a wiper. That wiper makes contact with the resistive track and can be moved by turning the knob. The wiper's position then determines the resistance between connectors 1 and 2 and 2 and 3. For example, if it's dead in the middle and our potentiometer is a 100K, then the resistance between these 2 and these 2 connectors will be 50K each. So by turning the knob, we're effectively able to change the ratio between these 2 resistances, which is why potentiometers are really just ready-made variable voltage dividers. If we send in our filter's output voltage here and connect this pin straight to ground, we'll get our divided down voltage from pin 2. But before we send it to our capacitor, we should really route it through another buffer. That's because a voltage divider will always be limited in the amount of current it can source or sink, since everything has to pass through this resistor. With a buffer, our capacitor can get filled up and drained as needed without any impediments. So first, I'll set up the potentiometer as a voltage divider. Then I'll turn this op-amp into a buffer and hook it up to the middle connector. Finally, I'll route the buffer's output to the capacitor. And yeah, we're now able to decrease the amount of resonance. How about increasing it though? To do that, we'll have to turn this buffer into a proper amplifier. We can get there by utilizing what we've just learned. If we replace the straight connection between inverting input and output with a voltage divider, we can force the op-amp to work harder. Here's how that works. Say we feed our non-inverting input a voltage of 5 volts. Then with a straight connection here, the output would simply have to match that voltage. But if we replace it with a 50% voltage divider, that output now needs to push out 10 volts in order to get the voltage here up to 5. Combining the feedback divider with an amplifier like that would then allow us to vary the amount of feedback from 0 to double of what we've been able to apply before. The proper amount of gain for the amplifier is something that should be tweaked to taste though. For now, we'll be using a 10K 6.8K voltage divider. All we have to do to implement that is remove the connection here and replace it with our voltage divider. And here's how that looks and sounds. Unfortunately, you'll notice that as I turn up the resonance, the sound gets distorted more and more, and in my opinion, not in a good way. So what's going on there? To get a better idea, let's check out how the amplified feedback looks here on the oscilloscope. So this is the signal we feed our capacitor. As I turn up the resonance, you can clearly see how it's being cut off at the top and the bottom, so that we lose most of the up-down motion there. What's the deal with that? Well, it's all about headroom. Since we're supplying our op-amp with plus and minus 12 volts, the range in which it's able to operate is strictly defined. This means that it can only accurately amplify signals if it stays within those boundaries. If we push it too far, the op-amp will basically get stuck at the minimum or maximum voltage level that it can put out. So what happens is that the cascading effect is ramping up so quickly and intensely that the op-amp runs into its limits almost instantly. To fix it, we have two options. We could simply lower the op-amp's gain. And this would eliminate the problem, but it would also limit the maximum amount of resonance we can add to the sound. The second option is much more viable, reducing the filter's input volume. Because if the input volume is lower, we'd slow down the cascading effect while also leaving more overall headroom for the resonance. How do we do that? We already know the solution, by combining a voltage divider with an op-amp buffer. You could of course use another potentiometer here if you'd like to experiment with the volume balance. But in order to keep it simple, I'll just use a fixed 100K 33K divider. Also, I've added two passive fixed frequency high-pass filters here and here. This time though, we're using fairly big capacitors and resistors, because we're only interested in making sure that the in and output signals are properly centered around 0 volts. Because if they aren't, we might run into more headroom issues. Imagine our input wave is swinging up here, with its center shifted upwards by 5 volts. Then our feedback amplifier will quickly crash into its upper voltage limit, causing the resonance to sound distorted and horrible again. To avoid issues like that, it's good practice to add high-pass filters to every audio processing module's in and output. So first, I'll route the input through a 1 microfarad 200K high-pass. Then I'll use the 100K 33K voltage divider to send it to our op-amp buffer. Finally, I'll add another high-pass to the output. As you can hear, the resonance no longer causes our filter to distort the signal. Instead, we're now able to drive it into self-oscillation territory. This is when the cascading effect gets so strong that it just never settles down. It will even keep going if I disconnect the input. This way, you can use the filter as a fairly decent sine wave oscillator. Now, you might have noticed that the resonance is quite dominant in the mix, especially at very high amounts. This is because we're letting the feedback run wild as much as it wants to. If you dislike the way that sounds, you can try tampering with the op-amp's feedback path. One idea that Korg used in their MS-20 filter design is clipping the feedback by using strings of 3 diodes like this. This might look somewhat confusing at first if you only think of diodes as one-way streets for current. Because then, this would simply turn our amplifier into a buffer. The trick here is that a diode only starts letting current through if the input voltage is above 0.7 volts. And this threshold adds up if you chain multiple diodes like this. So as long as the amplifier is operating in the range between plus and minus 2.1 volts, everything will work as usual because the diodes are blocking. But as soon as it tries to push beyond that, the diodes will start conducting and the gain will be lowered dramatically. This will do two things. First, it will slightly distort the resonance, which is an essential part of the characteristic MS-20 sound. And second, it will set strict boundaries for how loud the resonance can get. As a nice side effect, this will also allow you to use louder input signals for your filter, without it going into that ugly overdriven mode as before. This is because with the diodes, the feedback amp is much less likely to run into the supply rails and get stuck. So I'll add the 6 diodes to our circuit. This is a bit tricky space-wise, so I'll have to move to some empty area on my breadboard. And here's what that sounds like. I'll send a sequence to my oscillator so you get a better idea. So we made a lot of progress this episode, and I think sound-wise, this is quite serviceable. But there's still a few things we'll need to sort out. First, I've been neglecting the high-pass filter option. And second, the trickiest part is still on the horizon, making this design voltage controllable. So next episode, we'll first figure out how to adapt this low-pass into a high-pass design. And after that, we'll tackle the whole voltage control thing. Until then, you can get all the sheets I used this episode on my Patreon. There's a link in the description. Anyways, thanks for watching and I'll see you in the next one.